Okay, welcome everybody. This is going to be our first lecture on quantum theory for Physics 283. And we're starting off with the way in which quantum theory actually developed historically. And the first topic it's presented and we will present is the topic called black body radiation. And so before we start on that, I should probably discuss with you a little bit about what exactly we mean by a black body, and then secondarily, what do we mean by the black body radiation. The basic idea of a black body, such as the shirt I'm wearing today, which is I wore purposely for this lecture, is that a black body is a perfect absorber of radiation, of light waves, at all wavelengths. And it's a perfect absorber, meaning that it absorbs 100% whether you shine blue light on it or red light or green light. At room temperature, it is a 100% perfect absorber. Now, examples of materials that are commonly found of black bodies are things like lamp black, which is soot, some kind of soot that's found in chimneys, or charcoal, or the electric stove coil on your kitchen range, tungsten inside the old-fashioned light bulbs, not the new ones, of course. The spectrum of light coming from the sun follows what's called the black body spectrum. These are just a couple of the examples, but I wanted to make that point clear, but also that all bodies will begin to emit some thermal radiation that increases in intensity with the temperature. While at room temperature, my shirt is colder than its in surrounding environments, it will absorb the energy on it and the light, and so the white light does not reflect off of my shirt, and neither does any of the other wavelengths contained in the white light spectrum. Another property of a black body is a good absorber is also a good emitter, and meaning that as I heat up the body, it begins to, above ambient temperature, it will begin to radiate waves. And as it gets hotter and hotter, eventually those waves will fall into the visible spectrum. So the first thing we notice on a kitchen stove is the redness of the coil when it gets to be extremely hot. And those waves have now been, as we say, coming to exist primarily in the visible. And if we were to increase the temperature even higher, it would turn to a green and then later a bluish color, and eventually it would become what we call white hot, which means that we would be exciting all of the wavelengths in the visible spectrum fairly equally. So the emission spectrum of a black body is what is being studied when it gets heated up. When it gets heated up to a temperature that is well above what we would call ambient. At room temperature, they appear black, but as we heat them up, they begin to appear with these various colors as we get hotter and hotter. Now, typically, to get a material to respond with visible light, we have to get up to temperatures around 3,000 to 6,000 degrees Kelvin. Now, for those of you not familiar, a degree of Kelvin, or I should say, we should put it this way, that 0 degrees Kelvin is equal to minus 273 degrees centigrade. So the freezing temperature, which is 0 degrees centigrade, is plus 273 degrees Kelvin. Okay? So you can think of it as an offset. Nevertheless, these numbers are small compared to these numbers, so you can see that things that are in this range are quite hot, even to the touch. The other feature that we want to, or at least consider, is that to obtain a black body spectrum, the body's absorption should not depend on its wavelength. That is to say, it will absorb at all wavelengths, as we've said earlier. And also, the radiation from a black body does not depend on its shape or its chemical composition. So as long as it absorbs uniformly over all wavelengths, it will emit a spectrum of what we call the black body spectrum. And this spectrum is in some sense universal. And the observations of the black body spectrum dating back to 1900, because as you see here, Planck was the first one to study this, well, he wasn't the first to study, but he was the first one to actually come up with a theory to explain, and even his explanation needed to be adjusted by Einstein, who worked with Planck on this around the same time. So what does the spectrum look like? Well, the spectrum, if we were to plot the, let's talk about what the general picture of a black body. So suppose that I have an object that's held at some temperature T. If it's radiating away energy, we have to have a heat source to keep the temperature constant. And we want to, or we actually do observe, what is the intensity of the light. It could be a detector at some distance from the black body itself, where we can measure the spectrum of the radiation of light. And by spectrum, I mean the intensity versus wavelength. Now, there's a couple ways to quantify this. One of them is to use what's called the Poynting vector. This is the quantity we used in the optics portion of the class, or the wave theory portion in the earlier chapters. And this Poynting vector, defined in electricity and magnetism, is the what we normally call intensities, or watts per square meter. Now, oftentimes you will see the intensity of the spectrum plotted in terms of what's called the energy density of the electromagnetic wave. So U is the energy density of the electromagnetic wave. That might be worth writing out. U is equal to the energy density of the EM wave. Right? That is exactly what it refers to. And classically, the energy density, as we talked about in the earlier chapters, in the optics section, the energy density, according to Maxwell's equations, is given by a constant, epsilon naught over 2, times the amplitude squared of the electric field. So classically, this is an important point to keep in mind, the energy density of a wave is proportional to the square of the amplitude of the electric field. So those are a couple facts to put in mind. And what I've shown you here is that you can either express the intensity in terms of joules per cubic meter, which is the energy density. So imagine I have a cubic container with light reflecting and being emitted and absorbed inside, and inside that volume I have the electromagnetic field. There's an energy associated with that electromagnetic field, and in fact it can do work, such as when we hook it up to a solar panel, we can create electricity from that. The amount of energy available is proportional to the square of the amplitude of the electric field. And since the electric field the electric field contributes equally to the wave energy as the magnetic field, we've simply only specified the electric field component in this discussion. Okay, so what do we see? Well, we take an object which we believe is a black body. It's black at room temperature, and as it heated up, it begins to give an emission spectrum, and we begin to measure. We can measure S or measure U. This is, of course, the energy density. This is the classical idea of intensity that we've used. And measure this quantity as a function of wavelength. That is the spectrum. And measuring the spectrum, one finds that it rises up from 0 at very short wavelengths, and it reaches a maximum, and it falls back to 0 at long wavelengths. And the actual shape is shown better than the textbook that I'm drawing it here. But the key point is that regardless of whether I am looking at the spectrum of a tungsten light, a tungsten filament that's heated up in an electric bulb, or I'm looking at the spectrum from the sun or the electric stove, I get the same shape and spectrum. And furthermore, it was the physicist by the name of Wien who developed the empirical observation called Wien's law. And Wien's law says that I can predict by observation, he drew this conclusion, that the peak wavelength occurs inversely proportional to the temperature. So the law that he wrote down was that the wavelength in which I get peak intensity, right? This is the maximum level of intensity, times the temperature is equal to a constant. Okay? So his observation was that this number is a constant, 0.00293 divided by the temperature in degrees Kelvin. Okay, so that was the empirical status of black body radiation in 1900. Now, one can approximate a black body since as the book points out to you and discusses, there are no objects that are perfect absorbers at all wavelengths. Right? But one way we could ensure that an object is a perfect absorber is to create a small pinhole inside a hollow cubic cavity. And any light that gets in there will scatter many times off of the surfaces, and it will be trapped and have a very low probability of ever coming back out. So we can consider the pinhole as the black body and the radiation field inside as the radiation we want to study. Right? Now, let me draw one other conclusion from classical theory before we go on, and that is that the intensity, which I can specify as the S vector or the energy density, which is U, should only depend on E0. U is a function of the amplitude of the wave, and it does not depend on frequency. In other words, the energy density of the wave depends only on its amplitude and not on its frequency. And then there's a couple observations. Increasing the temperature of the object should only increase the amplitude of the EM wave. In other words, if I make the object hotter and I cause more energy density to be created from the black body, then that energy density only depends on amplitude and it does not depend on frequency. And furthermore, this in fact contradicts the observational fact that increasing the temperature does in fact increase the frequency of the radiation. So observationally, we get that the increasing the temperature causes higher frequency radiation, or we might say shorter wavelength, causes higher frequency radiation. This is in direct contradiction to the classical theory. Increasing the temperature will increase the energy density, which is to say U. That U is our energy density of the wave. And by the way, in this case right here, and as we will talk about later, we're going to describe U as the energy density inside the box. So I want to know the energy density of the electromagnetic waves, the light intensity, in joules per cubic meter inside the box. And for simplicity, we take a cube, and this is a hollow cavity. Yeah, I already said hollow. Good. And therefore, I can study what this is, and this will in fact be the spectrum, and I can observe the spectrum through the small hole in which some light escapes in a very, very small quantity. Furthermore, I can have a heat source here which will maintain the temperature of the cavity at whatever value I want to have. So this is the first contradiction. This does not agree, this statement does not agree with this statement, and so why is it that temperature changes the frequency of the radiation? It does not do so by a classical picture. So that was the first indication that something is clearly amiss and is not being accounted for correctly. Yeah, okay, so I could probably talk a little bit about what is the cause of the radiation. So what is the source of black body radiation? I mean, what causes it to emit radiation as the object gets heated up? Well, back in 1900, and as it is true even today, the theory is that the way in which radiation becomes created is that we consider the black body as, let's save space here and put it down here. We consider a black body as a conglomerate or a group of molecules of a group of ensemble of bipolar molecules. And so, for example, well, I'll pick one as an example which may or may not be the most accurate one to choose, but imagine that I have a molecule of sodium chloride. Right? Now, the sodium chloride will have an excessive abundance of, this will be an ionic, we call a ionic bond, which means that the chlorine is overall negative and the sodium is overall positive. So we can consider a bipolar molecule, for example, one in which these two atoms are held together by what's called an ionic bond, which means that one of the electrons from the sodium has been transferred over to the chlorine atom or spends more time in the chlorine and less time in the sodium. And we can think of these as being bounded as due to the attraction of the electrostatics. So, but on the other hand, if they get pushed too close together, then we have a repulsive force. So the idea is to model this sort of like as a spring, which becomes what we call a molecular oscillator. Right, okay? And Planck's theory of what was going on, and perhaps others at the time as well, is that when you heat up this, this material in the black body, composed of bipolar molecules, that the oscillation of the molecules begins to increase. And so as the temperature increases, then the oscillation, the amplitude of the oscillations of the vibrational motion, amplitudes of the vibrational motion also increases. And that is to say that the amplitude of the oscillation increases. Okay? The amplitude of the oscillation increases. So just like with electromagnetic waves, I have more energy available in an oscillation if the amplitude of the oscillation is, this will put in for an amplitude A, and of course the other one is oscillating in the other direction. Now, the result of an oscillating dipolar molecule is that it will emit radiation. So one of the things we know from E&M is that an oscillating electric dipole, well, irradiates energy, radiates EM waves. Okay, And that's exactly what we expect to happen, but therefore we get off this spectrum of light, and there will be many frequencies available, at least in the point of view of Planck's model, that there will be a spectrum of frequencies available given the nature of the black body. Now, the problem with that was that it doesn't really depend on what type of black body it was, but we were trying to look at still the idea that oscillating molecules, in particular bipolar molecules, generate electromagnetic waves certainly has a conceptual picture of how black body radiation is created. So the source of the black body radiation then is the group of bipolar molecules and the molecules that are oscillating at a frequency f. And by the way, they're oscillating at an amplitude A and frequency f. And furthermore, the frequency of the bipolar molecules is going to be equal to the frequency of the radiation. So that's the classical E&M picture. A dipolar molecule oscillating back and forth will radiate charge in much the same way as a dipole antenna will radiate electromagnetic waves. So that's basically the conceptual source of how these things are created. Okay, so now the next question is, how do we predict this spectrum? Okay, so to continue on with our discussion, the first thing I want to do is to write this spectrum out in a frequency space, in a versus frequency instead of versus the wavelength. And the reason is that, as we will see, the theory is more readily understandable when we interpret it as a frequency spectrum. Now, it's fairly easy to make that transformation because frequency is just c divided by lambda. So if I draw for example, my spectrum, and I have u of f and t, right? So the energy density of the electromagnetic wave, and for this case, we will consider it inside a volume V. Now, of course, the radiation is also radiating outside. This is a thin, hollow cavity, so it radiates inside, but it's also radiating outward. And the energy density will be the same regardless. So if I do this in terms of frequency, then I get that the frequency spectrum, which is now c divided by lambda. So for each lambda, I calculate frequency, and the intensity is measured as a function of frequency. So when we do that, then we get one spectrum, which is at, we will say, at T1. So I'll label this one as T1. And if I go up in temperature, I get a lot more radiation, which means that the area under the curve is going to be higher. But I also find that the peak moves according to Wien's law, and therefore that if I go to a higher temperature versus frequency, I get another curve such that T2 is greater than T1 as a function. So as a function of frequency, the curve is moving outwards. And that will be useful for us later on when we describe this in terms of the photon picture of light, which we're heading towards. But first, let me make one other comment that when we want to look at the energy or the energy density, then I can write that U is equal to the energy, which is a function of frequency and temperature, is going to be equal to the energy density of the wave. So I have the energy or energy density of a wave of frequency f, right, times the number of frequencies, we will say, in the cavity. between, this should be a T, between F and F plus dF, or we'll call it, dF. So given this is an infinitesimal, well, that is the way we'll write it. Now, we're going to concentrate mostly on this term right here, which is the energy density of a wave of frequency f. This one we said was proportional to the amplitude squared of the electromagnetic wave. Right? So before, and part of the problem with this is that the number of frequencies in the cavity increases. This term increases as the square of the frequency. We don't have to actually, I'm not going to be able to explain that to you right now, but it has to do with the boundary conditions that are on the wave within the cube. But for right now, I just want to look at this term, which is E0, or I'm sorry, the energy density of a wave. But in order to proceed, what we're going to do first is to look at an analogous, or what will become an analogy for describing the light field in terms of photons by looking at a box of, or an enclosure, a volume V of an ideal gas. And we know that in the case of an ideal gas, which I can also consider as a enclosed in a certain volume V, that within this gas, that if the walls of the gas are held at some temperature T, we can consider these gas molecules, or gas atoms, as moving around and bouncing around all the way throughout the box in various directions. And as they hit the sides of the box, they bounce off. And this kind of phenomena, where we've got a velocity distribution of the atoms in the box. So we have atoms with velocity v, or velocities, which we would say is a velocity spectrum with velocities that is a probability spectrum. We'll call it f of v. And furthermore, we know that for an ideal gas held at temperature T in a volume V, that the ideal gas law PV equals nRT is often used to describe how the pressure changes with temperature, or how the volume changes with temperature, or some other combination depending on which one of the three variables are kept constant. So in the case of an ideal gas, we've got the three variables are P, V, and T. Okay. Now, the theory leading up to this was first developed by Maxwell, who derived the equation for the velocity distribution. So this function f of v gives what's called the velocity distribution, and this velocity distribution rises up to a peak and falls back to zero. This is v, and this distribution of velocities, we should call this atoms with distribution of velocities, which we call f of v. And furthermore, if I increase the velocity of the atoms in the gas, then the spectrum increases. If I increase the temperature, then the velocities of the atoms increase, because the contribution, or what the term here, which we call pressure, is due to random velocity of the atoms, right? And the more energetic, or the faster the faster the speed or the velocities, this is really a speed distribution. But if I plot velocity on the horizontal axis, then if T1 is, if this is T1, then for any other temperature T2 greater than T1, then I will get a higher velocity. And hence this implies that the ideal gas will give a higher pressure. It's very similar to the idea that if you park your automobile in the street on a relatively cool day, and the temperature heats up from, say, 70 degrees to 100 degrees in a warm summer day, the pressure increases because the ideal gas law tells us that as the temperature increases, the pressure in the volume of the tire is also increasing, and this is due to the fact that the velocity distribution of the atoms is getting higher. We're increasing the speed of the particles by transferring the thermal temperature of the thermal property of temperature of the wall to the atoms in the gas. Okay. Now, already you can kind of begin to see where we're going with this, because with black body spectrum, we see that also there are two shifts in the curve, or there's one shift in the curve, I should say. As we raise the temperature, the spectrum moves to higher frequencies. In the case of an ideal gas, as we raise the temperature, the velocities of the particles become higher and higher. Now, there are a couple theoretical considerations that we have to look at to explain this phenomena, which then also applies to black body radiation. So the first thing I'm going to do is to tell you that the physicist Maxwell, who derived this black body, this velocity spectrum of an ideal gas, was able to put this in the form that f of v dv. So this is the number of atoms with velocity v, number of atoms with velocity between v and some number slightly higher than v plus dv, right? And furthermore, that this spectrum that he derived, he wrote down as there was a constant c we'll put out front, the kinetic energy of the molecule in the ideal gas. So the kinetic energy of the molecule in the ideal gas was 1/2 mv squared. This was divided by kT. And then there was an exponential term on here as well, which was e to the minus 1/2 mv squared. And by the way, we'll tell you what m is in a second. Mv squared divided by kT. And we have to now tell you what these values, what these constants are. So m is the mass of the atom. So m is equal to the mass of the atom. And 1/2 mv squared is the kinetic energy per atom. And then there are a couple other factors that we have to discuss, because these occur in the black body spectrum as well. The quantity K is called Boltzmann's constant, and we'll just write down for you that it's 8.64 times 10 to the minus 5 eV per degree Kelvin. Right? But more importantly, the quantity kT is equal to the average kinetic energy Ek per atom in the gas. Okay? And this, of course, as we said, was called Boltzmann's constant. And this exponential is called Boltzmann's factor. So e to the minus 1/2 mv squared divided by kT is called the Boltzmann factor. So we have to describe a little bit of this kind of theory, because at this point in your education, you have not had thermodynamics, so we're trying to incorporate this by giving you some of the key points, sort of like the cliff notes of what we would of what you would see in an actual course on thermodynamics. So this is the basic outline of what was used to derive the properties that the velocity distribution is increasing as we increase the temperature of the ideal gas. Okay? And furthermore, Boltzmann was able, and there's a derivation of this in the statistical thermodynamics that shows you how this was actually derived. We won't go into that. But this idea of KT, an average kinetic energy per atom, and a Boltzmann factor was now used as the next step by Einstein to explain the spectrums. Now we're ready to come to the punchline, which was the sort of the brilliant part of Einstein's contribution, which was that by the time Einstein got involved with this problem, he found a way to look at this a little bit like the ideal gas. So what happened was that Einstein viewed looked at the black body radiation. So I'll say black body. I'll say Einstein viewed the black body radiation in the cavity, in the hollow cavity that we originally talked about, as made up of particles. And these particles are made up of particles of light. Particles of light that carried a quanta of energy, that was proportional of energy that was proportional or equal to a constant times the frequency of the radiation. So the picture is the following. Classically, we have light as an electromagnetic wave, right? And I can describe this wave as an amplitude of an electric magnetic field. We draw the electric field. There's the amplitude E0. It's propagating along the direction with the velocity c. And this is, of course, exactly what I call the wave picture. And in the wave picture, the density of the radiation is equal to 1/2 epsilon naught times the amplitude of the electric field squared. Right? That is the energy density. Right? Now, the particle point of view basically says, now instead of considering this as a wave and with this being the energy associated with the wave, I can instead, I can consider this as being made up of a volume of particles called photons. And each one of these photons carries an energy, excuse me, E gamma equal to h times the frequency. So my subscript gamma is what I use to reference a photon energy, and there will be one of these. Now, if I have a certain density of these photons in the field that's traveling with the velocity, the speed of light, then the energy density I will have will be N, which is the number of photons per cubic meter per unit volume, right? Times the energy per photon. And in the limit in which I have a large number of photons in a very large wave, then this should be equal to 1/2 epsilon naught times the amplitude of the E0, the amplitude of the electric field. And this quantity right here, we're going to replace with h times the frequency. So this becomes N h times f, this of course being the number n, right here. This quantity being equal to h times the frequency, and this then is equal to the energy density of the wave. In other words, if I look at the phenomena as a wave, I should get the same result as if I look at the phenomena as a particle. So this is the particle view of light, and this is the wave view of light. This is the wave view, right? Now, sometimes I have to use one and sometimes the other. You cannot look at them both simultaneously to explain an event. The phenomena is either explained with the wave view, such as diffraction. Diffraction is a wave property of light. But we'll find out that there are particle properties that can only be described by treating light as a particle. So this kind of gives us what I would call a correspondence principle between the wave picture and the photon picture. Okay. Now, so having said that, then we now have to go and look at what happened after this assumption is made. So Einstein viewed the black body radiation in the cavity as made up of particles of light and carrying away a column of energy. So now the picture is very simple. We have the cubical black body structure with the pinhole, in which this whole object is elevated at some temperature T. So it is, by definition, radiating both on the inside and the outside of the cavity. And in particular, if we put a pinhole here, then we can look at the light that is coming out. So we will look at the radiation that is escaping from the pinhole, which is a sample of the radiation inside the box. The difference is that once we go to the particle picture, now what we're doing is saying what is really making up the energy of the electric field or the light field inside the box is photons bouncing around. And each photon is bouncing around in a different direction, and it gets absorbed and then re-emitted from the sides of the box, and these particles are called photons. Following the example of Maxwell, instead of having a velocity distribution of particles, I now have particles whose energy depends on frequency. So remember, with the particles over here, the atoms, the energy depends on the velocity, right? So the energy, which is somewhere here, we wrote down the average energy. So kT is equal to the average energy per atom, right? And by energy, we mean kinetic energy, and if the energies will have therefore a certain average or mean square of the velocity of the atom. So over here we have these photons, and these photons that are bouncing around have an energy E per photon. That's given by h times the frequency of the radiation. What do we do with that? Okay. Well, the way in which Einstein was able to complete the discussion of this is, now I need to take this off and remove this, was that, first of all, he says, okay, if it's true that each photon carries an energy equal to h times the frequency of the radiation, and notice you're taking a particle energy based on a wave frequency. This is the frequency of the wave associated with this photon. So the photon energy is equal to h times f. And furthermore, the probability, or the Boltzmann factor, is written as e to the minus nhf over kt. This is equal to the probability that there are n photons carrying hf of energy per photon. So he wrote down what we would call the Boltzmann factor, and then what he did was to sum up the total energy of photons in the box, the total energy of photons in the cavity, and he wrote this total energy as the sum of the energy carried by photons of a given frequency, which was nhf, times the probability that there were, in fact, nhf photons. Then we sum this from n equals 0 to n equals infinity. In other words, to find the one way of thinking of it as the average energy, or the total energy, is you take the energy for n photons, all of frequency f, you multiply by the probability that there are n photons of frequency f, and then you sum over the number of photons in each frequency from 0 to infinity. Having done that, and using this expression for Pn of f, so we write Pn hf, which is the probability that there are n photons of that particular frequency, that was given by the Boltzmann's factor. And this is completely analogous with the ideal gas in a box held at temperature T. All right? So now, okay, fortunately someone has been able to do this for us, and the result is that we get that the energy of the photons in the box, that this summation can be done with this exponential and simplified as HF divided by e to the HF over KT minus 1. And so this now becomes the total energy of the radiation inside a cavity of volume V. And the other factor that we now need to do to incorporate the final answer is to multiply by the number of frequencies between F and F plus DF. Now, we didn't really go into that or explain it, but basically it is an argument that the waves have to be periodic in space throughout the volume. In our case now, we have this volume V. So remember, the side of this cube is L. So the volume is equal to L cubed, which is the volume of which we just abbreviate as V. That's the volume of the cavity containing the radiation. And this term right here is proportional to the frequency squared times dF and the volume V. So if I take the total energy inside the volume divided by the total energy inside the volume divided by the volume, I get the energy density. So this gives me U, and U of F and T is a function that looks like F cubed divided by E to the HF over KT minus 1. And this is the derivation of the black body spectrum explained in terms of the photon picture of light, photon picture or view, and explained as the temperature increases, there are more photons with higher frequency, with increased frequency. Okay. This is exactly what we would expect, or what we hope to derive. And of course, there's a constant out here that I've left out, so we'll just put a big C up here for the constant. And this is the spectrum that we get. Now, I want to make sure I didn't make a mistake here on anything. So let me take a look at my notes. Yeah, I think we're good. So this formula now explains that as you increase the temperature, you now have more photons in the higher frequency range. So you're creating photons with higher frequency. And therefore, if I now look at this spectrum versus, let's call it HF. So let's replot this in terms of, instead of frequency, I'm going to plot in terms of H times the frequency, right? Then what this curve is telling us is that what is the number of photons? The number of photons at each frequency. And it follows exactly like the ideal gas law, which is telling us how many atoms there are at any given velocity. So on the x-axis, I have velocity, which represents, in some sense, the energy, or the square represents the energy of the atom, and that's increasing with temperature. And in this case, the photon spectrum is there's more and more photons with higher frequencies that are contributing.